KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Free bus for LKG to 8th standard.
Free, hygienic and nutritious food.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Education Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class, our interest is to find formula for magnification along with the rules while drawing the ray diagram in case of convex lens and concave lens. After that, one example problem based on the information what we are going to discuss, and then power of a lens. Power of a lens. What is the power of a lens? And what is the expression to calculate power, that is focal power in case of concave lens and convex lens. Okay, right. See here. So first we are going to discuss the rules to be followed and the important points we must keep in mind while drawing the ray diagrams for convex lens as well as concave lens. Okay, right. See this, ma. To find the image of an object by a lens, take any two rays from a point on any object. From a point on any object, trace their paths using the laws of refraction and find the point where the refracted rays meet or appear to meet. It is or appear to meet, right? That's it. So what he is saying, to find the image of an object, for example it is the object, this is the image, right? So to find the image of an object by a lens, take any two rays. So I already told you, from that object not 2 or 3 rays are coming, hundreds, thousands, lakhs of rays are coming. Each and every point of the object, from each and every point of the object, light rays are coming which are going to meet at a single point to give image. But for our convenience we are taking 2 or 3 rays. Okay, right. So to find the image of an object by a lens, take any 2 rays or 3 rays from a point on any object, trace their paths using the laws of refraction and find the point where the refracted rays meet or appear to meet, right? So here actually meeting, here appear to meet. Okay, right. So here the laws of refraction very important to keep in mind while tracing the paths of light rays from object to the image. Okay, right. So first law of refraction is incident ray, refracted ray, normal must lie in the same plane. Second law of refraction is the ratio of sine of angle of incidence to the sine of angle of refraction is constant. Okay, right. There itself, you know what is object distance? That is the distance of the object from optic center. And what is image distance? That is the distance of the image from optic center. And what is focal length? That is the distance of the focus from optic center. Because of having two curved surfaces, right, and due to the refraction of light, here we have two focus points. I mean, one is for one particular curved surface and another is for some other curved surface, right? So one is F, another one is F dash here. So H is the object and H dash is the image, right? Now, it is convenient to choose. It is convenient to choose. See these points, 3 points are very important. So you please be concentrate when I am explaining all the points one by one. See this. A ray emanating from the object parallel to the principal axis of the lens after refraction passes through the second principal focus in a convex lens or appear to diverge in a concave lens from the first principal focus. From the first principal focus. Okay, right. See this. So a ray emanating from the object parallel to the principal axis, parallel to the principal axis of the lens after refraction will pass. After refraction will pass through the second principal focus. See here, this is the ray which is parallel to the principal focus, which is parallel to the principal axis, is passing, will pass through the second focus, second principal focus, F dash. Okay, right. In case of concave lens appears to diverge. So here, in case of concave lens appears to diverge. Next, a ray of light passing through the optical center of the lens. A ray of light passing through the optical center of the lens emerges without any deviation after refraction. Without any deviation after refraction. Okay, see this. A ray which is passing, a ray which is passing through, a ray of light passing through the optical center of the lens, optical center of the lens without any deviation after refraction. So it is straight line because there is no deviation when the ray of light passes through the optical center of a lens, irrespective of concave or convex. Either in case of convex lens or concave lens, when the ray of light passing through the optical center, it will not deviate after refraction. Next, third point, see here. A ray of light passing through the first principal focus in case of convex lens or appearing to meet in case of concave lens emerges parallel to the principal axis after refraction. Parallel to the principal axis after refraction. See here. It is the light ray which is passing through the first principal focus. So it is first principal focus. After refraction, what will happen? It is parallel to the principal axis. No, it is the principal axis and this is parallel to the principal axis in case of convex lens. In case of concave lens also the same thing will happen. See this. So this is parallel to the principal axis. No. So after refraction what will happen? It will pass. So the extended ray back will pass through the principal focus. Okay, that is. So irrespective of type of lens, whether it is convex lens or concave lens, these are the rules to be followed while drawing the ray diagram. Right? While drawing the ray diagram means it is not a diagram, it is not the artificial diagram, it is the diagram which represents the position of light rays before refraction and after refraction, what happens practically. So in our physics lab or in our physics class, if you do the experiment with convex lens or concave lens, what happens exactly we are showing with the help of ray diagram. But I already repeated, but once again I am repeating. In case of practical situation, hundreds, thousands of light rays, lakhs of light rays are going to emerge from each and every part of the object to form an image. But while drawing on the blackboard, it is not possible to draw those many light rays. That's why we are taking 2 or 3 light rays. Okay, right. So keep in mind these 3 important points while drawing the ray diagrams. So these points we also discussed. In case of reflection of light, either it is plane surface or spherical surface. Here also whether it is plane glass plate or spherical glass plate, but the rules are same. So there we discussed in case of reflection. Here we are in a discussion in case of refraction. Okay, right. Next, magnification. You know very well, magnification is one of the important factor in case of lens, right? So in case of lens, in case of this optics topic, we need to see image of an object. So when we are in biology lab, right, we used to see bacteria and the smaller things, the order of micro, right? So there the image is the bigger than the object. That is our requirement and primary requirement, right? So not only that example, I can give many examples, but regarding all the examples, magnification is the very important. You can visualize. So whatever I am saying, if you think about daily life, what we are doing as a student and as a human being, you will get the importance of magnification in case of lens or in case of mirror. As simple as such, magnification is defined as the ratio of size of the image to the size of the object, right? So the same definition what I have given in case of mirrors, here the same definition I am repeating again. Magnification is defined as the ratio of size of the image to the size of the object. That you can write it as h dash by h here. So just by seeing these two pictures, and that is also you can write it as v by u, right? Okay. And you know what is the Cartesian sign convention? Including the Cartesian sign convention for erect and virtual image. Here you can see. This is the erect and virtual image, right? So that is what because of erect and virtual image formed by a convex or concave, right? Concave lens, M is positive, while for inverted and real image, M is negative. Okay. So we don't bother about what type of image will be formed because of convex and because of concave lens, because it depends upon the position of the object. Based on the position of the object, the nature of image and position of the image and size of the image depends. That we need not to keep in mind here. Here, in case of erect and virtual image, right? In case of erect and virtual image like this. In case of erect and virtual image, magnification is positive. For inverted and real image. Okay. Inverted and real image, here magnification is negative. So this is inverted and real. Inverted and real image, M is negative. Okay, right. So this is about magnification in case of concave lens and convex lens. Okay, right. Now we are going to see one example problem related to the information what we discussed. Okay, right. See that example 9.7. A magician during a show makes a glass lens with refractive index 1.47 disappear in a trough of liquid. Full stop. What is the refractive index of the liquid? Could the liquid be water? Right. So a magician, while giving a show, he showed one glass lens with refractive index 1.47, but it disappeared when he dropped into a trough of liquid. Right. What is the refractive index of the liquid? Could the liquid be water? That is the question, right? Okay. Now, see the solution, The refractive index of the liquid must equal to 1.47 in order to make the lens disappear. This is the statement, this is the conclusion. So to disappear the that is what lens, when he kept in a liquid, the refractive index of liquid must be equal to 1.47. That you can say that N1 is equal to N2. So when N1 is equal to N2, so in our previous class we discussed, 1 by f is equal to n minus 1 into 1 by r1 minus 1 by r2. When n1 is equal to n2, this gives us 1 by f is equal to 0. When 1 by f is equal to 0 or f tends to infinity. So when 1 by something by infinity is 0, no? So then f tends to infinity, right? The lens in the liquid will act like a plain sheet of glass, because you know the focal length of plain sheet of glass, that is infinitesimal, right? So that he is saying here the liquid will act like a plain sheet of glass because of the focal length is infinity. Now you can say that the liquid is not water. The liquid is not water. It could be glycerin. So based on this focal length, you can decide that based on the refractive index what they have given, we can decide that the liquid could be glycerin. Okay, right. Now we are going to discuss next power of a lens, focal power of a lens, right? So what is convex lens, what is concave lens, we are seeing, and how to calculate. So the next physical quantity, because already we discussed what is focal length, right? So now focal power, what is the focal power of a lens? See this, power of a lens is a measure of the convergence or divergence which a lens introduces in the light falling on it. So please try to understand, power of a lens is a measure of the convergence or divergence, right? Power of a lens is a measure of the convergence or divergence of a lens when light allows to fall on it. Suppose you take this right, suppose you take this convex lens, right? So when you take this convex lens, right, so the converging takes place. So how much convergence? Similarly, so we are going towards the measurement. Similarly, suppose for example in case of any of the lens, so generally in case of concave lens, how much divergence, okay, how much divergence, so that they can measure with the help of power of a lens, the quantity power of a lens. Okay, right. So next thing is, after that clearly a lens of shorter focal length, right, bends the incident light right. See here, so power of a lens, now we are going to discuss power of a lens. So power of a lens is a measure of the convergence or divergence which a lens introduced in the light falling on it, okay. So just you see that with the help of this quantity power of a lens, what we are doing, we are measuring how much convergence took place, similarly how much divergence takes place, how much convergence takes place and how much divergence took place, that you can measure by knowing the power of a lens. Next, clearly a lens of shorter focal length. So next sentence, clearly a lens of shorter focal length bends the incident light more while converging and diverging. So converging in case of convex lens and diverging in case of concave lens generally. So the lens which has shorter focal length bends the incident light more, right? So P is equal to 1 by F. You can say that, no, because shorter focal length means here bends the incident light more, right? Next, the power of a lens is defined as the power of a lens is defined as the tangent of the angle by which it converges or diverges a beam of light falling at unit distance from the optical center. So I will repeat once again, the power P of a lens is defined as the tangent of the angle by which it converges or diverges a beam of light A beam of light falling at unit distance from the optical center. Unit distance from the optical center, right? You see this picture, ma? So it is the convex lens, principal axis, incident light which comes here, and after refraction this will be the refracted ray, right? So if you compare, if you see the angle made by refracted ray with the direction of incident light, then it will be lambda. So geometrical mathematics, so when it is delta, this will be also delta. It is the focus point, it is the focal length, right? So it is the object. So the ray is parallel to the principal axis, means the object is at infinity, like that. Okay. So now tan theta is equal to opposite side by adjacent side. So tan delta is equal to h by f. H by f. If h is equal to 1, right, tan delta is equal to 1 by f. If h, mathematically, think mathematically, if h is equal to 1, tan delta is equal to 1 by f. Or for smaller value of delta, delta is equal to 1 by f. Delta is equal to 1 by f. Thus p is equal to 1 by f according to the definition, right? So when delta is equal to 1 by f, p is equal to 1 by f. Focal power is the inverse of focal length, right? So it is positive for converging lens, and negative for diverging lens, okay, right? Now what is the unit of focal power? It is diopter. Unit of focal power is diopter. Simply we are using a letter capital D to represent diopter. Next, power of a lens of focal length 1 meter. Power of a lens of focal length 1 meter is 1 diopter. You just write here 1 meter, ma. Then what will happen? 1 by 1 is 1. So if focal length is 1 meter, then so as simple as such, if f is equal to 1 meter, p is equal to 1d. And that sign of plus, or either it is plus 1d or minus 1d, depends upon the nature of the lens. If it is converging, plus 1d, if it is diverging, minus 1d, right? But numerically, when f is equal to 1 meter, p will become 1. It is 1d, because including the units diopter. Next, for example, because when we are going to meet eye specialist, he advised to take lens of certain focal power. So on the prescription slip, he will mention, the doctor will mention, so whether it is plus 1d or plus 2d or plus 2.5d, like that he will mention. Okay, so based on the intensity and the degree of eye problem we have regarding the seeing, regarding the sight. Okay, so there, suppose if it is, he mentioned that it is plus 2.5d, means the required lens is a convex lens of focal length 40 centimeters. Convex lens of focal length 40 centimeters. Similarly, if you mention p is equal to minus 4d, means here it will be, right, it is required lens is, for p is equal to minus 4d, means the required lens is a concave lens of focal length minus 25 centimeters, right? So this is for example, ma. So based on the focal power, we will decide the nature of the lens and focal length of the lens, what we need or we required. Okay, right? So in this class, we focused to learn what are the rules to be followed while drawing ray diagram. After that, what is magnification? So magnification is defined as the ratio of size of the image to the size of the object, or distance of the image to the distance of the object from optic center. Afterwards, magnification is positive for, right, magnification is positive for erect and virtual image. Erect and virtual image. Magnification is negative for inverted and real image. Then we discussed one example problem related to the information. Afterwards, we discussed what is the focal power of a lens. So in general, focal power is the inverse of focal length. What is the definition and what is the formula? What is the unit and examples based on the focal power? What is the focal length and nature of the lens? Okay, right.